Hi, everyone. It's good to see some names I met a couple of years ago in Volos. I would really like to greet in person, but unfortunately the circumstances are like that. Anyway, what I will present today has nothing to do with magnetic fields, as all the previous speakers spoke about. It has to do with photodissociation regions, and for short, we call them PDRs. And these PDRs are actually predominantly neutral regions which interact with the stellar far ultraviolet radiation in the energy regime of 6 to 13.6 electron volts. These are quite important because all the interesting chemistry, thermal balance, and evolution of the ISM may take place. And it's quite interesting to also to examine them in detail and see what we call the environmental parameters of the ISM look like. So to start with, to understand the evolution of the cosmic star formation process, we need to know the corresponding ISM molecular mass quantity galaxies. And one of the keys is to determine the distribution of species on large-scale objects, such as in a galaxy, for instance. However, there is evidence that the environmental parameters controlling the thermal balance of the ISM gas, such as the cosmic reionization rate, the FUV intensity, metallicity, etc., depend on the star formation rates. The star formation rate is known to evolve across the cosmic time and to have a peak at a redshift of around 2, as you see in this image here, which marks the galaxy assembly epoch. And also it is also known that this star formation rate is different within our galaxy when you compare, for instance, the galactic center with the outermost parts of Milky Way. The higher the star formation rates, the more energetic the ISM is. And that is the FUV intensity, the cosmic reionization rate, shocks, X-rays are all stronger than in regions where the star formation rate is low. Observations, on the other hand, provide us with plenty of different emission lines, which we use to constrain these ISM parameters. The most commonly used of these parameters are the different transitions of CO, which, as you see in this figure, have different distributions for different galaxies. So the key question that we want to answer is how do these observables depend on each ISM environment? There are many different groups that have been working on this question for many years, studying these diagnostics in 1D, 3D simulations, etc. In this regard, we have also published recently a new and fast algorithm which we call PDF-Chem, and that estimates the average imbalances of species using column density distributions as an input. What I will show you today actually is results from 2 different 3-dimensional PDR simulations. And to do that, we also need some initial conditions. So these initial conditions are taken from a series of papers led by Benjamin Wu in 2017, who examined cloud-cloud collisions. So there are 2 MHD simulations here, which are, as you see, there are 2 clouds that we have in different times. The upper case is the colliding, so they have some velocity, and in the bottom we have the non-colliding case, which evolves simply because of turbulence. We will not consider all of the snapshots. We will only consider the last snapshot, and actually a sub-region of this snapshot because of memory consumption issues. As computational astrochemistry is quite memory intensive. So we will call from now on the uppercase a dense cloud, which is about to give birth to new stars, and the diffuse cloud, which is the average ISM GMC. So here we are, we have the dense cloud, which has approximately 43,000 solar masses. The diffuse cloud has 14,000 solar masses. They are 14 by 14 parsec squared, the area as you see here. So each side, so computational size is 14 parsecs. And what we have done was to take these 2 clouds, we embedded we use the 3D PDR code, we embedded in many different combinations of ISM parameters. We actually used 4 different cosmic reionization rates in the range of 10 to the minus 17, which is the average galactic one in the Milky Way, up to 10 to the minus 14, which we meet in the galactic center and also in the early universe. We have 4 different FUV intensities from 1 to 1,000, and 4 different metallicities from 10% solar to twice the solar, so supersolar metallicity. So we end up having 20 simulations. We have 10 conditions for each of the density distributions. We have 2 distributions. We have 20 simulations. We will use a fiducial as fiducial ISM conditions. These, so we have 10 to the minus 16 cosmic reionization rate, a 10 G naught, and a metallicity. So if we vary, for instance, the cosmic reionization rate, and we want to see how the diagnostics look like, we always keep the G naught and Z the same. So if we vary one ISM parameter, we keep the other 2 fixed. In the paper that we actually present a lot of results. I have no time to go through all of those. You're welcome to see the paper. What I will show you today is actually emission of different coolants, the most important coolants for the dense cloud, as well as the column density of molecular hydrogen and the gas temperature maps. And for both clouds, I will show the CO sleds, the spectral line density distributions, line ratios, conversion factors, which are quite interesting. But as you see here in the main paper, we have many different other results. So let me guide you through these maps. So each column corresponds to the value of the free parameter, which in this case is the cosmic reionization rates. So we have here 10 to the minus 17, 16, 15, and 14. And as we go in each, and as we go down, each row gives us a different result. So we have the C+ emission at 158 microns, C1, 10 transition, CO, 10, and then the column density of molecular hydrogen and the density weighted gas temperature here. So as the cosmic reionization rate increases, the emission of C+ increases, and for 10 to the minus 14, which is the higher cosmic reionization rate, the cloud is entirely connected. The emission of the C+ is entirely connected with the H2-rich gas, the molecular gas. There are 2 reasons behind this. So the first one, that the abundance increases of C+ due to the destruction of CO by cosmic rays. And the second is because the gas temperature, as you see down here in the filaments, becomes quite warm. It approaches like 50 Kelvin, 60 Kelvin. So you approach the 91 Kelvin excitation temperature of C+, and as we are close enough to it, C+ suddenly increases its emission. So we may have a molecular case, a gas which is fully molecular. Cosmic rays heat up the gas, it approaches 50 or 60 Kelvin, and then becomes suddenly C+ bright. Therefore, that's why you see this sudden increase here. Now, if we move on to the C1, 1 to 0, the atomic carbon line is this one. So it is also increasing as a function of the cosmic reionization rate, and it is well connected with the H2-rich gas as well. This supports earlier suggestions that it remains a good tracer for molecular hydrogen. The emission line of CO1 to 0 shows a somehow different behavior. So first, let us focus on the high density region of the filaments, or if you want, the core, so where these yellow vectors are. High cosmic rays make it brighter because cosmic rays destroy CO in the lower density medium surrounding it, making it possible to see through and hence detect a stronger emission. This means that if a region is inundated by strong cosmic ray energy densities, it may appear quite clumpy. Now, on the other hand, the emission of the more diffuse medium decreases for the cosmic reionization rate up to 10 to the minus 15. So we see here this small island, if you want to say, this small island of ISM. So it disappears here, disappears completely, and then appears again. So we have a non-linear relationship between the cosmic reionization rate, which is actually the beauty of astrochemistry, being quite non-linear. So this is because the CO, the molecule of CO, is forming back to its molecular phase via the OH channel. We have actually examined exactly this effect in one of the earlier papers. So as we increase in the gas temperature, CO is able to form back again through this OH channel, which is quite interesting to consider. Now, the column density of molecular hydrogen remains remarkably unchanged at all times. So finally, the gas temperature increases by increasing the cosmic reionization rate, as I mentioned earlier, and you see here that we have a quite warm gas in the filamentary structure. Similar effects are also observed with the FUV intensity. So the C+ emission increases, and it always originates from the diffuse ISM. The C1 line 1 to 0 also increases as a function of the FUV. And the CO here, because of the photodissociation of CO by the FUV photons, we see that the outer parts of these clouds do not emit in CO 1 to 0 because CO is gone through the photodissociation. But we have also quite bright regions which stay in the filamentary structure because FUV photons have been severely extinguished. And also, yeah, this region now disappears more and more. So the column density of molecular hydrogen also remains quite unchanged, and the gas temperature remains unaffected inside the dense filamentary structure, but in the outer parts where the column density is low, we have that the FUV radiation heats up the gas and causing all this interesting chemistry. And finally, when we talk about the metallicity, the C+ emission slightly increases for metal pure gas. So in this case, you have to read the map from right to left in the opposite direction. So if we decrease the metallicity, C+ increases, C1 also increases, CO is destroyed in the outer parts also because dust is not there anymore, and it cannot block the FUV photons, so the CO is photodissociated. The molecular hydrogen is also dissociated. We have more samples of H1 atomic hydrogen, and the gas also getting hotter and hotter. So these have direct effects with the diagnostics. Now, of course, the CO 1 to 0 is also presented here, but we have actually examined the CO up to 10 to 9, so the first 10 transitions. But it's interesting to see how all these 10 transitions behave. And for that, we use the spectral line inertia distribution. So the x-axis here in all cases is the upper state of CO line. So this is 1, 0, 2 to 1, 3 to 2, etc. And on the y-axis, we have the total emission that comes from the cloud. Remember here that we have both clouds now. The dense cloud is marked with solid line. The dashed is the diffuse cloud, so the second cloud with the more GMC look-alike. And what we see here, the take-home message from that one is that the more the dense clouds is, then all the CO sleds are brighter. But the interesting thing is that the high JCO lines appear to increase only when we increase the cosmic ionization rates, and which is also quite interesting when we do extragalactic ISM, when study extragalactic ISM, because the high JCO lines can tell us, can tell us a lot of things regarding the ISM conditions. We examine also different line ratios. I would like only to focus on one of them, which I found quite interesting, which is the atomic carbon line. Again, the solid line is the dense cloud, the dashed line is the diffuse clouds. What we find is that this line ratio is quite sensitive to the cosmic ionization rate and also on metallicity, and not on the FUV intensity, which can be used as a degeneracy breaker if we want to combine it with CO sleds and examine more closely the ISM conditions. And this is actually quite excellent news for the upcoming CCAT Prime telescope, because the CCAT Prime telescope, as you may know, will be dedicated on the to examine the atomic line emission of Milky Way and other galaxies. The final thing I would like to point out is actually the conversion factors. So the factors that we use, because we cannot observe molecular hydrogen directly, we have somehow to estimate the mass, and we use CO for that. So how this conversion factor of CO behaves across different environmental conditions is a good question. And also, what about the atomic carbon as a molecular gas tracer, because it becomes now more and more popular. So what we find is that the cosmic ionization rate does not really change the XCO factor. And also the FUV radiation does not also changed a lot, the XCO factor, but when we go to metallicity, then we find a lot of and strong differences there. And actually, when we go to subsolar metallicity, like 10%, as you see in this diagram here, we see that we have the solid line, which is the dense cloud here, and the diffuse cloud is up here. So just because of the density, we have an order of magnitude or more difference in the XCO factor. And this is in accordance to, in agreement with the observations by Andreas Schruba in 2017, who measured this conversion factor in low metallicity environment and found these differences just because of the density distribution. So this is also in agreement with our models. I will leave you with my conclusions. The main conclusion, if I summarize all the presentation in one sentence, is up here, that the carbon cycle is much more sensitive to the ISM environmental parameters than the atomic to molecular hydrogen transition is. So thanks a lot.
Thank you, Dr. Bisbas. Any questions for Dr. Bisbas? We have time for a few questions. The first one is by Gina Panopoulou.
Hi, Hema.
Hi, Gina.
So what strikes me is that the clouds have very different morphologies depending on all these parameters. And so what I wanted to ask is, have you quantified the effect of, cosmic ray energy density or ionization rate, or the FUV radiation field on the morphology in some way? Have you measured the widths of filaments to see how they appear in these different tracers?
No, as far as I understand your question, it may be related with combination of these models with hydrodynamical simulations, or just because of the just in these snapshots.
Just because of chemistry, I'm wondering what the how different would filaments look like in the absence of hydro effects, and if you know of hydrodynamical effects or other effects.
Oh, I honestly don't know that because yeah, I'm a little bit confused about your point. So so you're asking if how the filaments would look like in different environments or in different conditions of the ISM?
So yeah, so if we look at observations, CO filaments versus dust emission filaments have different widths. And
the widths, okay.
Yeah. So I'm wondering if you quantified, or if you can quantify,
No, we didn't measure this. Okay. We didn't measure this, unfortunately. And yeah, that's actually a good point. So perhaps we need to post-process for that several, I suppose, MHD simulations which have filamentary structures, and then see these differences. I presume that this will have definitely to do with velocities, of course. So it will be interesting to see how this also connects. When also the lines become optically thin or thick, depends also on that. On the environmental conditions can also make one line more optically thin or thick. So the width will be different because you will see more material. So unfortunately, I don't know the answer to that, but this is a good point.
Just to be clear, thanks. Were the simulations you used isothermal, or did they include H1 to H2 transition?
No, the MHD simulations that I showed here, these simulations included some minimal PDR chemistry, minimal. So they're not isothermal. They have some equation of state, which is dictated by some minimal PDR chemistry. And the temperature that I showed later on, which was actually, for instance, here, this is an output from 3D PDR. So this is actually the true temperature, if you mind, if you want. So this gas temperature is not in the hydrodynamical simulation, but the hydrodynamical simulation uses a close enough temperature distribution.
Got it, thanks.
Okay.